Thank you. Hi everyone. My name is Emmanuel Libao. I'm a PhD student from KAIST in South Korea, and I'm glad to be here to present our work entitled MeshGraphNetRP, Improving Generalization of GNN-based Cloth Simulation. Current state of the art about using deep learning for cloth simulation mostly focused on mapping body pose with garment. Shown here are two works from last year, Neural Cloth Simulation and SNUG. Both works use body pose or pose history as an input to their model. Emphasis on these works lies on capturing the effects of body movement on the garments, rather than the dynamics of the cloth occurring beyond body-induced deformations. Generally, these methods are inherently limited to handling tight-fitting garments, and also they must be trained for each garment type or topology. Next, here is the main reference paper we took as inspiration for our work, MeshGraphNets. Published in 2021, MeshGraphNets showed the capabilities of GNN in learning cloth dynamics. It shows here impressive results. However, we can see that the cloth itself does not move. The movements are caused by external force like wind or an obstacle like a ball. For our work, we are able to improve generalization of GNN cloth simulation models that learns the cloth dynamics wherein the cloth can move freely in 3D space. Shown here are the results of our work on different scenarios. We see the rich dynamics of the cloth present, like in the long cloth, where the handles are moving separately. Also, we see here the triangle cloth bouncing, and here a wide cloth moving spirally upwards. Here is an overview of our whole pipeline. We gather data for making the graph containing physics-inspired features. We use this to train our GNN model, which is used in runtime. First, let's discuss the data. Shown here are the different trajectories you use for our training dataset. We used ArcSim Cloth Simulator for this. The trajectory uses a square cloth with 1024 vertices, and it only includes 14 translation trajectories and 2 rotation trajectories. We are able to learn the model properly using only these motion trajectories. Next, we discuss about the graph. We make input graphs from the training data consisting of node features and edge features that consists of physical properties. For the node features, we introduce the external force and kinetic energy. For edge features, we changed the rest state representation from 2D to 3D, and we also included stretch and bending definitions on the edge features. For more details, please refer to our paper. Next, we discuss about training. So we use the same encoder processor decoder architecture as MeshGraphNets. However, we changed the encoder from MLP to RNN to consider the historical state of the cloth. The processor is a critical part of the model where message passing occurs, wherein neighboring vertices pass information to each other. Finally, the decoder would output the acceleration for each node, which we use to get the next frame positions of the cloth. Here are the physics-based laws we introduced alongside the original acceleration laws from MeshGraphNets. We introduced the kinetic energy laws, edge vector laws, edge length laws, bending laws. We also used a technique called scheduled sampling to gently introduce rollout on the training, which made the results much more stable. For more details about these, please check our paper. Lastly, we discuss about the runtime. In runtime, we would only need the initial mesh and trajectory of the control handles to run it. Our model can be generalized on motion direction, either translation, rotation, or a mix of both, and also motion topology and motion speed. Our final model that uses RNN with 10 input sequence length runs at 27 FPS. MeshGraphNets runs fast at 83 FPS, but has unstable results, which we will show later. And finally, the ArcSim, where we got our ground truth data, runs slowly at an average of 2.5 FPS. Let's check next the performance results. Shown here are the comparison of our work with the MeshGraphNets model. We compared our work with MeshGraphNets and also MeshGraphNets with the scheduled sampling technique. We can see in Figure A the huge difference in the position RMSE of MeshGraphNets and our work for full rollouts. Looking closer between our model and the MeshGraphNets with scheduled sampling, we see a huge gap on the edge length RMSE between these two. Shown here are the video results. We see right away that the MeshGraphNets and MeshGraphNets with scheduled sampling cannot produce stable results. We can see the instabilities occur on the elongation on the part near the cloth handles. Also, there is shaking artifacts here. Again, let's see it. And our model is stable. Shown here are the ablation studies. The first figure shows how well the RNN encoder performs throughout the training compared with the MLP encoder. The second figure shows the performance when we remove each of the introduced physics feature and loss. The effect is very evident when we remove all the added features and loss on the model. So we can see here the edge length RMSE difference. It shows how physics-informed features greatly improve the performance of our model. Shown in this video are the comparison between MLP encoder and RNN encoder. We can see clearly that the MLP encoder results in stiff cloth as it rests, whereas our model that uses RNN encoder behaves dynamically like a real cloth. Okay, next, I would like to show a screen capture of our live demo in Unity. So here is a square cloth. So we can see here on the left side the different keys that I was clicking, and the cloth can translate in X, Y, and Z direction using these buttons. And here is the current FPS that the model outputs. And also the model can rotate in the along the vertical axis and horizontal axis, shown here. In actuality, the training dataset are gathered in 60 FPS. When we hit replay, we can see how the output moves in its real FPS. So now it moves in 60 FPS. So as said earlier, our model can move freely in 3D space, as shown here. We can combine translation in different axes and also even add the rotation at the same time with translation. So we can see it here. And then let's see the replay. Okay. So also, our model can be generalized on different topology with different numbers of vertices. Here is a quarter cloth that is 1/4 the size of the training square cloth. We can see that with fewer vertices, the model can output the results more quickly. And here is the replay. And here is a long cloth topology that has twice as much vertices as the square cloth. With more vertices, the model outputs the results slower. And let's check the replay. Okay, here is the replay. Also, our model can handle configurations with more than 2 handles that are not seen on training at all. Here is a white cloth with 3 handles, with an additional handle at the center. See it moving. And replay. And here is a triangle topology with all the top vertices acting as a handle. So also, our model can also infer different speeds outside the training data speed. So here is the replay of the output when the maximum speed is half of the default. So this is 0.5 times. Of course, if the cloth moves too much faster than the default speed, the result would be unstable, as shown here. The cloth is moving twice as fast as the default speed, we can see that the rest of the cloth cannot keep up, but when the cloth stops moving, the cloth would return to stability. However, but still, even with until 1.2 times faster than the default straining speed, we can see that the model can still infer the correct dynamics of the cloth. So, as conclusion, we propose a novel GNN-based cloth simulation framework that leverages physics-informed features, RNN encoder, and scheduled sampling in the networks. Our model are able to show rich dynamics for a cloth moving anywhere in 3D space, trained with only a sample of possible directions. Our model could also generalize for arbitrary planar topologies and control handle configuration. We acknowledge that more complex cloth motions, such as colliding with complex objects and also dynamic changing of handles, may present a challenge for deep learning-based methods. Exploring these challenging scenarios would contribute to advancing both deep learning architectures and cloth simulation studies, ultimately leading to more robust and versatile cloth simulation frameworks. Thank you very much for listening. If you have questions, you can email me here.